Greetings everyone, welcome to Side A, Side B. We're a little late with the video. We had a touch of strep throat, so our voice could be a little scratchy in this one. But here we are. In this video, the inverse function and its characteristics, the overall plan, discussion, and doing examples. So what's in our toolbox? How about background work and previous studies? This discussion will lead to a walkthrough of arc cosine and arc sine. At the same time, it's going to lead us into our next period, which is linearity. That being said, these discussions about foundational concepts are leading to bigger and better things. Like we said before, it's going to be a work in progress, especially trigonometry, because there's so much to unpack. Some of our videos assume viewers have the background knowledge to follow along, although sometimes we do not assume, like if it's a concept walkthrough, and sometimes it's a walkthrough for Side A, Side B, like learning new concepts or clarifying previous ones. And it's in our opinion, linearity or inverse could lead to a discussion about spirituality or philosophy, because we could exit the negative and then enter the positive, or equivalently, undo an operation. But here, Side A, Side B, we're sticking to the mathematics. So, we hope you'll stick around. Maybe you'll get something new. So, what's an inverse function? There's actually two words to unpack, inverse and function. First, what's a function? For the most part, a function can be considered as a machine, like a transformer or a duplicator. We input a value, the function returns an output. What do we mean by transforming? Perhaps the best example of a transformation is when a caterpillar transforms into a butterfly, because the butterfly can no longer be considered a caterpillar. The caterpillar has transformed into something completely new. That being said, a function could transform a value into a new value, such as a 1 to a 2 or a 3 to a 4. What do we mean by duplication? A function could return the output value the same as the input value. Coming up, we'll consider a function that just transforms, just duplicates, or it's possible to define a function that does both. A function blue1 is typically written as the following, read as f of x, although we can name the function g of x or h of x. That equals whatever expression or expressions we have in terms of x. The next step, we can define what type of inputs and outputs our function accepts, then returns, respectively. Like maybe our machine just accepts quarters, but nowadays machines accept paper money. We define what our mathematical machine accepts and returns, simply writing the inputs I and outputs O are in the element of the natural numbers, which are the numbers 1, 2, 3, 4, and 5, and so on, which are integers. With another step, defining the domain of the inputs, which is the closed interval 1 through 6, denoted with the square brackets. We'll define the range of the outputs shortly. Observe our function is in two sections, two rules, or it has two openings to process two different inputs, such as if our input x is an even number, insert into the opening of the function x. If our input x is an odd number, insert into the opening of the function x plus 1. See that? Like, if you happen to put an odd into the even opening, imagine the machine spitting it back out, along with the digital message does not accept. Let's find the outputs. We have the first input, the odd number 1, then the machine returned 2. Then, the even number 2, the machine would also return 2, followed by 3 and 4, 4 and 4, 5 and 6, 6 and 6. At first, it might seem our machine has a duplicating issue. However, for a function to satisfy the definition of a function, or our definition of a function, because somewhere in the universe a function could be defined slightly different. To make life easy, let's stick with ours. It's possible to have two output values equal each other, as long as each of them originate from a unique input value. So recall, our machine was absolutely correct in rejecting the odd into the even opening, because if it did, we'd have one odd returning two same outputs, and that would violate our definition of a function. Now we can define a range for the outputs. First, observe the range contains only even numbers. If that's the case, we could use set builder notation, which is not shown here, but we could write it in such a way that it would articulate that the outputs are even numbers. Or since we have a restricted range, we could just list the specific even numbers as blue 4. Simply, the range is the set 2, 2, 4, 4, and 6, 6 for the only 6 even natural numbers of the range. Before moving on to graphing the data, upon inspection, we can safely say the inputs satisfy parameters 2 and 3, and the outputs satisfy parameters 2 and 4. Would you agree? If so, the last thing to check, our function to be a function must pass the vertical line test. But before we do that, let's graph the data. The first column is our data, the second column is the plot of our data, and it's possible to have a graph with just points, for a good reason too. Just consider the way we typically plot the graph of a function, such as a continuous unbroken curved or straight line between, say, 2 points. The line constitutes the set of all the points of our inputs and outputs, or more formally, the points x and y, respectively. Then regard, the terms odd and even are mathematical definitions that only apply to integers, and an integer is a whole number with no fractional or decimal component. In contrast, a decimal number has a fractional part represented by digits after the decimal point. It follows, because decimals are not integers, they cannot be classified as odd or even. Since no integers are found between any consecutive integers, there are no other integer solutions between the points 5, 6 and 6, 6. The same can be said for the other points. Look at column 3. The red circle is implying there's a multitude of inputs that return the output 6. But after what we just said, we should be very confident this is impossible. The base plot is also impossible for the way our function is written. As a result, for a good reason, we have just points as our plot. In column 2, it means if we insert a decimal into any of the two openings, our machine will reject it, along with the message, invalid. Irrational numbers are also discounted because they have decimal expansions which are infinite and never repeat in a predictable pattern, such as pi, although it's possible to approximate pi with a fraction. Remember, our function, and, for that matter, any function, must pass the vertical line test, which means no single input returns the same two outputs. Looking at our graph, it looks like we have what we want, but use an actual line to test. The first point checks. As does all the points. Nice. Which is why our machine rejected the odd input in the even opening. Still, our function does not pass the horizontal line test, which doesn't eliminate it as a function. However, it counts it out as a one-to-one function because two unique inputs returns the same output. Next, what's an inverse? Have you ever wished you could undo something sometimes? Like maybe something you said in haste?
Look, I'm sure you already know this. I did throw that game. After I did it, I felt so shitty I wish...
Or anything else? Well, according to mathematics, it's possible. In theory, anyway. Although some walk faithfully believe it's actually possible. In mathematics, inverse refers to a concept where one operation or function undoes an operation or action of another function.
So it looks like I'm gonna get to know you guys a lot better, because I ain't doing that twice in a lifetime. We got a little time left. We can still do this.
Resulting in the original value. This is evident as inverse operations like addition and subtraction, or as inverse functions where applying the original function and its inverse in sequence returns the initial input. And actually, ever since grade 1, we've been working with inverse operations, so we should be quite familiar with them. The procedure was just named differently. First, let's unpack and clarify operation, undoes the operation, and original value. For example, if we begin at the number 0, the original value, followed by the summation operation 0 plus 7, then perform another operation, sum positive 7 with negative 7. As a result, the additive inverse undoes the effect of the positive 7, resulting in the original value 0.
Sorry, guys.
Yeah, me too.
Yeah, me too.
All right, now let's get started.
So mostly, for an entire football game, we're doing and undoing operations. To underscore that idea, another example, the multiplicative inverse. If we begin with the number 1, the original value, multiply it with 9, returns the rational number 9 over 1. Then perform the multiplication operation, multiply it with its reciprocal, 1 over 9, found by flipping the fraction 9 over 1, or just swap the numerator and the denominator. As a result, the multiplicative inverse undoes the effect of multiplication, resulting in the original value 1. Nice. Now we can start to understand the definition of inverse. The first part, operations that reverse each other's effects. Next, let's clarify undoes the action of another function in sequence which returns the initial input. Let's take each in sequence then. The first bullet, the inverse of a function f of x, is denoted in the white box, read as f inverse of x. The notation looks like a superscript for a power, but it does not represent the reciprocal 1 over f of x, like in the blue box. Rather, the inverse notation signifies the function undoes the original function. Next bullet, if f of a equals b, then f inverse of b equals a. Very nice, because this property shows applying an input to the function f and then applying its output to its inverse in sequence will return us to the original input. See that? In short, the output b of the original function becomes the input of the inverse, and vice versa. Now we have a working definition of an inverse function. The second and last part, ladies and gentlemen. What do you think? Which is f inverse, denoted by the notation in the white box, undoes the action of the original function f of x. Now, let's discuss its key characteristics, which include: the original function must be one-to-one, also called injective, which means, just like a function, each output corresponds to only one unique input, with the added condition no two different inputs of the domain map to the same output in the range. Recall, we did a non-example of a one-to-one function. Input-output reversal. The inverse function swaps the roles of input and output. We've seen an example of that already, where f of a equals b, then the inverse of f equals a. Domain and range swap, which is just an extension of the input-output reversal, which means the domain of the original function f becomes the range of its inverse, and the range of the original function f becomes the domain of its inverse. Graphical reflection, which means the graph of f of x and its inverse are reflections of each other across the line y equals x. The composition identity, which essentially means when you compose a function with its inverse, the result is the original input x. Lastly, undoing operations. To be clear, we've seen examples of undoing operations such as addition and multiplication. Here, we're referring directly to the operations of the inverse function, which performs the operations of the original function, but in reverse order. Before a deeper discussion in the next section, let's do a brief walkthrough of the key characteristics. Sounds good? If so, we invite you to stick around. A function must be one-to-one, also known as injective, to have an inverse. This means no two different inputs produce the same output, like in our non-example. Sorry, ladies and gentlemen, that's a no-no for an injective function. The following are examples of injective functions, such as example 1, the cubic polynomial, which is known as the basic or parent cubic function. The second is known as the identity function. Both of them will pass the vertical and horizontal line test. Observe, the cubic function transforms and duplicates, because just consider 0 returns 0, 1 returns 1. It duplicates, but not in the basic sense of the word, because here's something that's interesting. The identity function seems to be a special case, as the only one-to-one function that duplicates, but unlike in our non-example, duplication with the condition, each input returns a unique output. Next, the composition identity. There's actually two ideas to discuss: composite functions and a mathematical identity. More on that shortly. For now, we'll just say the composition identity of an inverse function is the principle when a function denoted in the white box by f and its inverse are composed and vice versa. The result is the identity function x. The input and output reversal property. We've already done an example. Essentially, the inverse function swaps the roles of input and output, such as if f of a equals b, then f inverse of b equals a, which naturally leads to its extension. The domain and range swap property of an inverse function states the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function. In essence, the inputs of the original function are the outputs of its inverse, and the outputs of the original function are the inputs of its inverse, which is a natural consequence of the input-output reversal property. You know what, ladies and gentlemen, coming up, if we need to discuss and elaborate more on some of the characteristics, we will, On the other hand, if it's redundant, for some, we can skip to save some work. Second from last. Let's go with a visual for that. The graphical reflection over the line y equals x. Essentially, the graph of an inverse function is the graphical reflection of the original function's graph across the line y equals x. We have e to the x as the red plot, and its inverse, the natural logarithm ln x, the green plot. This reflection property means that for any point xy on the original function's graph, the point yx will lie on the inverse function's graph, such as the point 0, 1 on the red plot is reflected with the point 1, 0 on the green plot. When a function and its inverse are graphed, they are mirror images of each other across the said line. And actually, the exponential function e to the x is a great example of a one-to-one function that just transforms, and we can prove it in the next section. To clarify the blue box, many times we'll see log x base e written as ln x. Lastly, the undoing operations property of an inverse function states, by applying the inverse function to the output of the original function, returns the original input value. However, in order for this property to happen, means the inverse function performs the opposite operations in the reverse order of the original function, which will revert the input back to its original state. For example, in the white box, if f of x equals y, the function multiplies by 2 and then subtracts 4. In the blue box, f inverse equals x. Now the function will first add 4, then divide by 2. To see how that works, consider the system of equations of blue 1. Observe equation 1. F of x equals y. See how we got equation 2? We solve for x in equation 1. Then if we let x equal 0 in the red box, in blue 2, we apply it to both equations. In blue 3, we can solve for y, which equals negative 4. Then apply it to equation 2 as the input. We have 2 plus negative 4 over 2, which equals negative 2. Then positive 2 plus negative 2 just equals 0. After applying algebra that sequenced the operations of the original function f of x in reverse order, we applied the output of f of x to f inverse, which returned the original input value 0, checks with the yellow. That's a lot to take in, so if that still doesn't make any sense, more discussion coming up, like actually proving a function is injective. We're guessing 2 more videos, or if we have to, 3. As it were, seeing how far we can push the undoing operations of an inverse function. Let's begin.